Okay, so hello everyone. My name is Miloš. I'm also here from the faculty. I'm a PhD student, and I work at the laboratory for photovoltaics and optoelectronics. So today we've already heard a bit about integrated photonics and what they can do, and I'm going to add on to that with another more specific topic regarding the design of optical couplers for integrated quantum dot single photon sources. So first I'll just do a brief introduction to build some context into this work, and then I'll show three approaches of designing such an adiabatic optical coupler. Alright, so why are we talking about single photons in the first place? I'm sure everyone here has heard more than once that quantum technologies nowadays are a very common topic both in research and otherwise. And the base element of any quantum system is a qubit, or perhaps rather some sort of quantum state, which can be implemented in a number of ways. One of those is by using photons, but to implement a quantum state we need to be able to create and manipulate single photons. And one way to do that is with photonic integration. So if you want to use photonic integrated circuits for quantum applications, we need to be able to integrate different quantum photonic devices, such as single photon sources, perhaps some modulators, single photon detectors, and some memory onto a single chip. And then once we are able to do that, we can use these QPICs for various quantum applications. But the current issue is that there doesn't exist a single fabrication platform that is capable of integrating all of these devices monolithically. So we're left to look to other solutions. And that's where the microtransient printing project comes in. Now I'll be honest, we didn't coordinate very well who'll do the introduction for this project, so this slide is there's perhaps no need to go into details since Draj and Professor Dries have already gone into this project. But maybe just to reiterate quickly, the main idea is to use microtransfer printing to enable to create a platform for quantum photonic integrated circuits. And of course the main workhorse here conceptually is the microtransfer printing process, where we use an elastomeric stamp to transfer individual devices or arrays of devices from the respective source wafers onto a common interposer platform. And in our case in this project, we're using a few different platforms, including lithium niobate, silicon nitride, and gallium arsenide. So this process can be used to achieve physical integration, but we also have to ensure efficient optical coupling, especially since quantum technology, when you're dealing with single photons, it's very expensive even to lose one of those, right? That's the world we live in. So here we're using adiabatic couplers, or maybe another term you might have heard is adiabatic mode transformers, which is in essence this section highlighted here. So in this example we have a gallium arsenide waveguide shown in yellow with a quantum dot in the middle. And this waveguide lies on top of a silicon nitride waveguide. So this would so the top gallium arsenide waveguide would have been microtransfer printed on top of this silicon nitride. And as the quantum dot emits photons, they're first confined in the gallium arsenide, and as they propagate towards the end of this gallium arsenide taper, the mode in which they exist is pushed down into the silicon nitride waveguide. But since efficiency here is of key importance, we also have to consider different fabrication related effects which can be detrimental to the performance of these couplers. For example, microtransfer printing misalignment, then perhaps critical dimension loss which can arise in lithography, bonding layer thickness deviation, and also in this case scattering losses due to waveguide roughness, which in gallium arsenide can be quite high. Okay, now moving on to three approaches how we might design such a coupler. First, some background, or rather some parameter definitions. So the wavelength that we're using is 930 nanometers, which is the center wavelength where the quantum dots emit photons. And here I also would like to point out that the taper length, although in theory, in an ideal world, the longer the taper, the lower the losses. Once you account for scattering losses and other processes, it turns out that, of course, there's a trade-off. So if you make a long taper, you'll have lots of scattering losses, but the coupling efficiency might be good. And if you make a short taper, the coupling efficiency might suffer, but you'll have less scattering losses. So here we limited ourselves to 50 microns. And the target optical coupling efficiency, as specified in our project, is more than minus 0.2 dB. Now here on the right is the cross-section of this device, and also the fabrication error parameter definitions. So these are the three parameters that we considered in our analysis. So first is the misalignment, the lateral misalignment of the two waveguides. Then there is a gallium arsenide width error, which can occur in lithography, and also BCB thickness variation. So nominally, the BCB thickness would be 50 nanometers, but it can vary by some amount. Okay, so a basic approach might be to simply use a linear taper, 50 microns long. Here in the right figure, on the y-axis is the coupling loss, and on the x-axis are different combinations of the fabrication error parameters, with this leftmost most column showing the ideal case. And we can see that in the worst case, we get about 0.8 dB loss. And if we also add an estimate of the propagation loss, we get an estimated worst case loss of over 1 dB. Now the reason we initially only considered these three parameters is because these are easily included in our optimization process, whereas the the propagation losses here mainly include the scattering losses on the waveguide sidewalls. These are more difficult to include in simulation, so initially we're only looking at some sort of estimate. Okay, so here we see with a linear taper, worst case loss is much higher than our project target, but luckily, as it turns out, we can, in the beginning of this taper and at the end, we can taper more rapidly. And as a consequence, we achieve a much better performance. So this example here was manually optimized for the ideal case, and we can see that here we get almost perfect transmission. And while in the other fabrication corners, we might get, on average, lower losses, the worst case is still quite high, which brings us to about 0.99 dB loss. And now the third approach that we considered is a global optimization algorithm. It's nothing special, but it does allow us to more easily include different optimization goals, for example, optimizing for different fabrication corners, and also it allows us to divide our taper into more segments, which of course gives the optimization more degrees of freedom to work with. And so you can see here in the ideal case, and also in the fabrication corners, we get performance well below the project target. However, if we include the scattering losses, we get up to about 0.44 dB, which is still much better. Future, we're hoping that we might also optimize this taper in respect to the scattering losses, and that might get us below this 0.2 dB goal. Now we're also planning an experiment in the future. So the plan is to fabricate a few different taper designs, optically characterize them and compare compare the performance. And here's just an example of what a gallium arsenide coupon that is ready for microtransfer printing looks like under a microscope. So this line in the middle is the gallium arsenide waveguide, and these sort of needle structures to the edges are the tapers, which are part of the coupling sections. In the middle here, in the waveguide, there would be the relevant quantum dots, which would be used for single photon emission. And in this case, there are also some metal contacts which can be used to apply an electric field. To the quantum dots. But for the case of our experiment, so in terms of characterizing the tapers, this active part would not be needed. So here we'd really only be focusing on these tapers and ensuring that they have good and reliable performance. And with that, I conclude my talk. Thank you.
Thank you, Miloš. Any questions? Yes, please.
Can you compare the integration technique that you're doing here with what would be offered, let's say, at AIM Photonics? So with this, how do you call it? Yes, that, yes.
Compare it with lipstick?
With integration options that AIM offers, AIM Photonics.
I'm unfortunately not entirely up to date with what AIM offers.
Okay.
But I imagine it might be some...
I don't know, I'm just trying to understand, pros and cons and so on.
Perhaps I'm not the best person to speak to regarding this, but one of the advantages of microtransfer printing, for example, over perhaps wafer bonding, is a much better use of the precious material, because you can more densely pack your devices on the, I don't know, your 3.5 wafer, for example. That would be one. Then let me think. I can't think of anything at the top of my head right now, but perhaps we can also discuss it afterwards. I can look it up.
Yeah, if you knew something, that would be great to talk about. Okay, thank you.
Yeah.
Okay, so yes, please.
So in the end, all these papers, they look pretty similar. So not a linear one, but this one and the previous one
Yes.
look pretty similar seen from here. Can you explain where the difference then is after the optimization? What makes it then?
That's a very good question. I haven't been able to perform a detailed analysis of which features exactly give the better results. But in theory, it should be that so the coupling strength between different modes in the taper will depend on the immediate width in the cross section of the gallium arsenide, and you need to taper very slowly where the coupling strength is strong, and also it's difficult to put into words. So if you look at the different cases here in the fabrication corners, the critical points around the taper will vary, because the conditions where the critical points arise are different, because they're different, the cross section is different, and the global optimization algorithm is good at optimizing this, while when we try to do it manually, it's much more difficult to ensure that in every case we'll have slow tapering where the overlap integrals are high, so when the coupling is strong.
Okay, thank you.
That's a good answer. I'm not sure.
Okay, let's thank the speaker once again.